In Chapter 2, Section 6, what we're going to do is we're going to look at several different basic function shapes. And these have distinctive shapes which we'll use later when we're working with more complicated functions. So having some knowledge of these basic shapes can be very helpful when you're trying to analyze functions or when you're trying to match a function with data. Let's look at the first one. First function is just f of x equals x. That's about as simple as you can get to have something that's not a constant. This is called the identity function because all it does is the output is exactly the same thing as the input. Whatever you put in, that's what you get out. Example, if you make an xy table, if you put x equals -2, you get y equals -2. X equals 0, you get y equals 0, and so forth. If you graphed this function, it would just be a straight line with a slope of 1 that goes through the origin. It would look like this. This type of equation increases everywhere over the entire domain. The domain of this function is -infinity to infinity. All straight line functions that have slope will have a domain of -infinity to infinity. They will also have a range of -infinity to infinity. This function is continuous. What that means is there are no gaps in the function. Every point connects to another point on the graph. Second type of function, or second function, is the squaring function, which is just f of x equals x squared. We raised the exponent on x by 1. This is no longer a linear function, so it's no longer a straight line. If you calculated some values, put a -2 in for x, you get 4 out for y, and so forth. When you graph that, what you get is the familiar shape of the parabola. This parabola has certain specific characteristics. The vertex of the parabola is at the origin. That vertex is this extreme point, the minimum in this case. The vertex opens upward. It decreases if you go from -infinity to 0. It increases from 0 to infinity. The domain of this function is -infinity to infinity. However, the range goes from 0 to plus infinity. This is the basic x squared function, a basic U shape. Next we have the cube, which is f of x equals x cubed. And xy table, if you graph that, it has a distinctive S shape. A couple of points about this. For the basic shape, it goes through the origin, because if you plug in x equals 0, you get y equals 0. The basic shape also has the right-hand side going up and the left-hand side going down. It increases over the entire domain, and the domain is again -infinity to infinity. In fact, something we find is that if the function is a polynomial function, in other words, the defining expression is a polynomial, then the domain will always be -infinity to infinity. The range will not, but the domain will. The cube is also continuous over its entire domain. Now, for the cube, domain is -infinity to infinity. The range is also -infinity to infinity. This is different from what we saw with the square function. Next, we're going to look at going the other direction with our exponents. Instead of increasing the exponents, we're going to start fractioning them. So in this one, this is like x to the 1/2. In other words, take the square root of x. That's the function. When you start trying to plot this, you have some issues you must deal with. Square root, we cannot plot the square root of a negative number. That's an imaginary number which you cannot plot. Therefore, for us to have a function, we have to restrict the values of x which we can allow in the domain. Therefore, our domain cannot have negatives in it. It can have 0 and it can have positive, but it cannot have negatives. So our domain goes from 0 to plus infinity. If I plug values in from 0 to plus infinity for x, then this is what I get for y, taking the square root. Now you notice, to make it easy, I plugged in perfect squares here so that when I took the square root I got whole numbers. If we graphed this, we would get a line which looks like this. We do not have any values, any part of the graph over in this part of the grid where x is negative, because it does not exist there. The domain begins at 0 and goes to plus infinity. The convention that we all work with in math is that anytime we take a square root, we're always going to get a positive number. Therefore, the function, which is the square root of x, we must always get a positive number here. That means that we not only do not have values of the function here, we do not have values of the function down here either. The function only exists in this first quadrant. It begins at the origin and goes up. It is increasing over that entire domain of 0 to infinity. It's continuous, but it's flattening out. It's not getting steeper as x increases. It's getting shallower. It never actually flattens all the way to horizontal. It's always increasing, but it does continue to bend over. The next function we're going to look at is the cube root. And because with odd index roots can always have a negative radicand, because if we take a negative radicand and raise it to an odd power, we will get a negative number. Therefore, an odd root of a negative number will give a negative number as the root. For instance, if we plug in x equals -8, the cube root of -8 is -2, because if I took -2 and cubed it, I would get -8. Therefore, the function, the cube root of x, exists for all x's from -infinity to infinity. It also has a distinctive S shape. Like the cube function had, the cube root function has an S shape also. There is actually a relationship between the cube and the cube root, which we'll talk about later when we talk about inverse functions. The domain of this function is, as always, -infinity to infinity. And the range is also -infinity to infinity. It increases over the entire domain. It's always going up. It is continuous over the entire domain. All of the functions we've looked at so far were x raised to some exponent. Now let's look at something a little different, the absolute value function. You all know what the absolute value function does. It takes whatever is inside and makes it a positive number. So if we took values of x, -2 would become +2, -1 +1, 1 would remain 1, 2 would remain 2, etc. When you graph this, you get this very distinctive V shape that is distinctive of the absolute value function. Points about this: the vertex here where the two lines meet is at the origin. The slope of this right-hand side is plus 1. The slope of the left-hand side is minus 1. The function exists for all x, and it's continuous for all x. It decreases when you go from minus infinity to 0, and increases from 0 to infinity. The domain is at minus infinity to infinity. The range is 0 to infinity. Very distinctive shape. We'll see that and use that in several places. Then we'll start looking at some more unusual types of functions. There is a type of function which is called piecewise defined, and it's called piecewise defined because in different parts of the domain it has different equations defining it. This is an example of a piecewise defined function. This function is defined as f of x equals minus 2x plus 5 if you're in the part of the domain that's less than or equal to 2. In other words, from minus infinity up to 2, my function is going to be defined by minus 2x plus 5. Once I get to 2, once I start above 2, then I change my defining function, and my defining function is just x plus 1. If I graph that, it looks like this. This line over here is minus 2x plus 5. If x equals 0, then it's 5. The slope, if I go over 1, I go down 2, and so forth. When x equals 2, minus 2 times 2 is minus 4. Minus 4 plus 5 is 1, so it's at 1. So this point, 2 and 1, is on the graph. As soon as I move immediately to the right of 2, then I'm no longer on this line, I jump up to this line. If you recall what the closed circle and the open circle mean, they're like brackets or parentheses on intervals. This one means that that point is part of this line. This line goes all the way to include that point. The open circle means that the line does not include its own endpoint. The endpoint is here, but it's not part of the line. If it were there, if it were part of this line, then I would not have a function because I would have two different values when x equals 2. So I cannot allow both of these to contain that point. In this case, it's defined such that this line contains the point, this line does not contain the point. This function decreases from minus infinity to 2, it increases from 2 to infinity. It is not continuous. There is a gap at 2. One rule of thumb way for checking continuity is, can you draw the complete function without lifting your pencil off the paper? If you can draw it, it's continuous. If you cannot draw it, it's not continuous. In this case, the only way I can draw this function is to lift up my pencil and then put it back down there and continue. This is an example of a piecewise defined function. It has some very useful characteristics. We'll see an example shortly. Here's another piecewise defined function. A little bit different though. In this case, we're defining it by this expression if x is less than 1 or equal to 1, by this expression if it's greater than 1. If you graph that, it turns out this equation, if you allowed x to equal 1, that would have the point 5 on the line. This one, we can allow that. Well, 2 times 1 plus 3 gives 5. So this close point is actually part of this line. This line has an open circle there so that you don't have 2 points, 2 different points. This is continuous. but it has two different definitions depending on where in the domain you are. One that's really strange is called the greatest integer function. Greatest integer function uses these weird looking double brackets here. Here it is in a little different font. But those are double brackets which have very special meaning, and they mean that whatever is inside, I'm going to calculate the value of what's inside and then take the largest integer that's equal to or less than that. If what's inside equals an integer, I'm going to take that value. If what's inside equals a mixed number, I'm going to take the whole number part of that. So the greatest integer less than or equal to the value x. What that looks like, here's some examples. If I plug -2 in to here, well, -2 is an integer, so the function is equal to -2. But if I plug -1.5 in, that's not an integer. If I want the greatest integer less than or equal to that, I have to move to the left until I reach an integer. If I move from -1.5 to the left, the first integer I encounter is -2. Therefore, the value of the greatest integer function at -1.5 is -2. I can, if I go to -0.99, that's not an integer, so I have to move to the left. Moving to the left, the first integer I find is -1. So the value of the function at -0.99 is -1. So on. If you keep doing that for all the values in the table, and then you plot that, and you plot enough values, you'll get this rather strange looking graph. It looks somewhat like a stair step, but there's nothing connecting the steps. They're hanging there in space. On these, the left end of the horizontal line is part of the line, because the greatest integer less than or equal to -3 is -3. But the greatest integer less than or equal to -2.5 is still -3. I cannot move up to the -2 line until x equals -2. So I keep coming along here until x equals -2, and I'll suddenly jump up there, come along here until x equals -1, then I jump up there, and so forth. This function is not continuous. It's constant on the intervals from -2 to -1, -1 to 0, and notice the closure on these intervals. Bracket on the left end, parenthesis on the right end. So it's constant within each of these intervals, but as you go from interval to interval, it's discontinuous. It's at all integer values of the domain. So every time you have an integer along the number line here, you have a discontinuity in the function. The domain of this function is -infinity to infinity. No matter what value of x I substitute into the function, I can calculate an f. But the output will always be only an integer. The output will either be -3, -2, -1, 0, 1, 2, etc. It will never be a mixed number or a fraction. Example, slightly different example to show how this changes as you put different things inside. Let's put 1/2 x plus 1 inside the greatest integer brackets. In order to evaluate this, we need to look at what happens when we put different numbers in. Let's first look at the interval from 0 to 2. If x is 0, then what's inside here is equal to 1, and so the greatest integer less than or equal to 1 is 1. if x is 1. Then I have 1 times 1/2, that's 1/2. 1/2 plus 1 is 1.5. That's not an integer. The greatest integer less than or equal to 1.5 is 1. So at 1, I'm still at 1. In fact, as I keep moving up, I'm 1 until when I hit the integer 2, then I have 2 times 1/2 is 1. 1 plus 1 is 2. That's an integer, and so I jump to 2. Some examples of that: if x equals 0, y is 1. If x equals 1/2, y is still 1. X equals 1, and so on. Put those into a graph, and the graph of that function would look like this. It looks very similar to the previous one, except now my intervals are 2 units long rather than 1 unit long. That's because of this 1/2 multiplier right here. So they're 2 units long. They still go up 1 unit at a time. The greatest integer is always going to step up 1 unit at a time. That's just another example of how that can change as you substitute in different expressions inside the greatest integer brackets. Example of where you might use a function of that type. This is actually a piecewise defined function. That's what the greatest integer function is. This one is similar to a greatest integer function, but it doesn't look exactly the same. This example is like a FedEx or a UPS, and if any of you have used that, you know that for anything from 0 up to some weight, you pay a fixed fee. No matter how heavy it is, it can be almost nothing, or it can be right at the limit, then you pay the certain amount. Well, this particular company, anything 2 pounds or less is $25. So 1/10 of an ounce would still cost you $25. 2 pounds cost you $25. But if you go 1 fraction above 2 pounds, then they're going to charge you an additional $3. So 2.01 pounds would be $25 plus 3 is $28. And then when you went above 3 pounds, they charge you an additional 3. Then above 4 pounds, an additional $3. And so what we want to do is we want to represent what this function would look like that defines those costs. We're going to let D be the cost of sending a package that weighs X pounds. And we want to graph it from 0 to 6. We're not going to graph it at 0 because you wouldn't mail something that there's nothing there. That's what 0 weight would be. So we do it, we don't do it at 0, but we go from there. Okay, if we're in the interval 0 to 2, that's the first one. For anything 2 pounds or less, we have $25. Soon as we step up anything above 2, we bump the rate up by 3. So it's 25 plus 3, or we get $28. Soon as we get to 3, we bump it up another 3, so it's this 28 plus 3 more, or 31. And you can continue on. Every time your interval bumps up by 1 more pound, you bump the price by $3. If you graph that, it would look like this. From 0 to 2 pounds, it's $25. And notice on this one though, my open circle is on the left because you're not going to mail 0 pounds. There's nothing to mail. And 2 pounds would still be in this basic rate. But as soon as we get anything above 2, we jump up to $28. And anything up to and including this 3 pounds is $28. Since we go above, we jump to 31, then 34, then 37, and so forth. Every time you go up by 1 pound, you jump up by $3. I want to make a point, or just point out something about this graph. In this graph, the horizontal axis goes from 0, 1, 2, 3, 4, so just a normal axis. But look at this vertical axis. It's 0 here, but then it's 20 here and 30 here. Those are not uniform. Notice this little squiggle in the graph. That little squiggle there indicates that a section of that axis has been removed. Section of that axis has been removed. They're not showing a big part of this axis.